It's really exciting to be here. So I'm going to talk to you about the latest paper I worked on, Object-Centric Learning with Slot Attention. This is what I worked on during my internship at Google Research in Amsterdam. So really to start like from far away, like in representation learning, we typically assume to have access to high-level observations, such as this very pretty picture of Switzerland. And the goal is to learn a function that maps these observations into a low-dimensional vector representation. And ideally, this representation should contain all information about the observation so that you then can train a classifier on top, and then the classifier is going to be accurate and have a bunch of interesting properties. And the key underlying assumption here is that the observations are not truly high-dimensional, but are in fact manifestation of a set of low-dimensional ground truth factors. When we talk about object-centric representation learning, we mean learning representations that separate objects, concepts, entities, or pretty much anything that you can think of that classifies as node in a graph. And I want to make a little digression on disentanglement. Before working on slot attention, I worked on disentanglement for a couple of years. And this is not explained in the paper, but I want to give you some perspective on why I became interested in this object-centric learning and how I see slot attention fitting into like this narrative of building structured representations. So if we go back to the example I made earlier, the goal of disentanglement is to essentially align the representation with the ground truth factors, so that if you perform a change on the ground truth factors, then the representation should change accordingly. And there are two ways of looking at disentanglement. The first one is the maybe more classical one, where you have these images, and then you assume that the images are the result of some mixing of some independent factors of variations. So we assume there's no confounding factors, everything is independent. Another way to look at this, and this is how my advisor at MPI, Bernard Schokop, think about all this, is that you have a structural equation model in causality. I'm not sure if you're familiar with this. So basically you have a graph with parent-child relations, and then you model these relations with a functional assignment, and this is a structural equation. And this induces a causal factorization, which is the factorization of the joint distribution of the variables according to the graph. And then one can see disentanglement as recovering the noise variables. And this is interesting in order to like answer specific interventional and counterfactual questions. However, like when you like look back at the type of pictures that I showed in the beginning of this talk and the type of data sets that we actually use in disentanglement, well, they are remarkably different. And I'm not just talking about like texture and the higher resolution, but even just the complexity of having multiple objects and even multiple instances of the same object. And it's actually pretty unclear how to go from single objects to modeling like more complex scenes, and how can we represent multiple objects, even if we throw away the very high resolution and the complicated textures. And what I would argue is that this limitation is actually very fundamental, because like we've been talking for 2 years about disentangled representations, but at the end of the day, we still train a convolutional neural network, which takes as input a picture and outputs a vector. So in this vector, there's an implicit ordering of the dimension. And if you now start thinking about having multiple objects in a scene, means that the objects are going to be ordered in the representation, which actually doesn't make any sense, because objects are not naturally ordered. So what we would rather want to have is a more modular architecture, where the output is not a vector, but it's a set. So that we don't impose an unnatural ordering. And further, I mean, convolutions work very well, but what we would rather like to have is on-demand computation, and we really want to instantiate only the variables that we actually see, and share knowledge between these variables. What I mean here is that if I learn to extract an object from a scene, well, then I should be able to extract two objects from the scene and classify them using the same classifier on top, because like I know how to classify from a single object to like which material it's made, for example. But also I should be able to change the number of objects like quite freely, because at the end of the day, like I care about learning how to recognize objects, and not just like restricting myself to outputting like a vector from an image that contains a single object. That doesn't mean I learned anything about objects. So the missing piece here is really how can we connect like low-level information, like perceptual like features, with high-level variables that are suitable for reasoning and causal reasoning if you're into this type of things. And in particular, we want to train everything end-to-end. And this is how I personally see slot attention. So slot attention fits into the family of slot-based object-centric architectures. There are a bunch of other like related works here. But the key underlying idea for this family of architecture is that you have your image, you do some low-level processing with a CNN, like a small CNN backbone, and then there is an abstraction step where you go from the output of the CNN, which is structured as a grid, to a set of high-level variables that are supposed to capture the objects in the scene. And then if you want, you can have some reasoning on top, for example, comparing these variables. And at the end, you have some task, which depends on these slots. And for the purpose of this talk, I'm gonna focus on the grouping, and we are also not gonna have any type of reasoning. So this third step is not present. So slot attention is a differentiable interface between distributed and set representations. It takes as input like a feature grid and outputs a set of task-dependent high-level variables. And it does so using an iterative attention where there is competition, so that the query of the attention mechanisms like specialize on individual objects or high-level entities. The core prediction problem is, as I said before, this mapping from grid to set, and each element on this set should capture an object, some part of an object, or some part of the background. And you can think of slot attention as being very similar to capsule network, with the key difference that in our case, slots are symmetric, meaning that they're also fully exchangeable. What I mean here is that in principle, slots act as object files. They can in principle bind to anything in the input. So it's not that the first slot always binds to cube, the second slot always binds to spheres. And that's what CaptureNet will do. And the reason why we don't want to have this specialization of the slots is because as soon as you have that, then it becomes very problematic to deal with multiple instances of the same object. Unless you go back to convolution and you do kind of like convolutional capsules, where you look whether there's an object in different locations of your feature grid. What we want instead is to have these like high-level variables, and in principle can bind to anything. And you can really think of them as like variables in a programming language. So slot attention, to go a little bit more into the details, look as follows. It takes as input the feature map, to which we add position embeddings. Then we initialize the slots by sampling them from a normal distributions, with mean and standard deviation, which we learn. And mean and standard deviation are going to be shared across all the slots, meaning that we have one Gaussian from which we sample, in this particular example, like 4 slots, in the example here on the right. So now we have these 4 slots, and we have this iterative procedure. So first, we take the dot product between a projection of the inputs and a projection of the slots. And then we compute some weights by taking the softmax with some temperature. And this is essentially the regular dot product of attention, with the key difference that the normalization here is not on the input, but on the slots. So this is equivalent to this is the inverted dot product attention. And the intuition here is that since you normalize on the slots axis, you create competition for the slots to split the input. And then we take a weighted mean between the weights and the projection of the input. In a regular attention, this would be a weighted sum. But in regular attention, you also normalize with respect to the input. So in this case, we take the weighted mean because otherwise this creates instabilities during training because of the scaling and the fact that the input is not normalized anymore. So now we have these updates for our slots, and we change the value of the slots with a GRU. And in practice, to make training a bit more stable, we also use a bunch of layer norms here and there, in particular on the input and the slots, to make sure that the gradient flows well through the module. And now if you stare at this pseudocode like a little bit, you will realize that this is essentially the same as doing soft k-means. Soft k-means is the same. You have these slots, which are the centroids. You sample them randomly, and then you compute some scores, which is then, in this case, Euclidean distance, and you don't have these projections. And then the weights is the same. This is basically the assignment of the points to the centroids. And then you take the weighted mean, which is basically recomputing the centroids. And then you don't have this GRU, you just replace the value of the old centroids with the value of the new centroids. So you can really think about the slot attention as a meta-learned clustering, where the slots compete for explaining the input, and the clustering is meta-learned because the objective function has this like learned projections, and the optimizer, which is the GRU, as this meta-learning. So basically, you can think of it as for each example, you're going to cluster the features and produce these abstract variables. So slot attention has 2 key properties, which are depicted in this equation here on top. The first one is that it's permutation invariant with respect to the input, meaning that as regular transformers is suitable for set-to-set processing. The main difference is that the input and output sets, can have different cardinality. But then when we want to do grid to set, then we need to add position embeddings. Otherwise, we lose the positional information due to the permutation invariance. And the second property is the permutation equivariance with respect to the slots, which means essentially that if you change the order of the slots after initialization, then the output of slot attention is just going to be in a different order. And this is important because this is really what makes slot attention respect the set property, where slots don't specialize because they're sampled randomly. And at test time, you can even change the number of slots because they don't specialize. You can just sample more slots and run the algorithm with a higher number of slots, for example. And this is why yeah, they act as object files and really learn this common representational format. So in the paper, we explore two tasks, set prediction and object discovery. I'm going to start with set prediction because that's what I've done. And Thomas did the object discovery. So a set prediction, the setting is like this. You have this input image with multiple objects, and you have the usual backbone, the CNN backbone, and then slot attention. And now slot attention is going to extract a representation for the individual objects. And now you can add an MLP on each slot. And here we share the parameters. So we apply the same MLP to all the slots. And this MLP is going to predict the properties of the objects. For example, it's a rubber cube, it's gray, and it's at this particular position. And we train this supervised. So we have ground truth labels for the object properties. And now we need to match the labels with the predictions because this is a set prediction task. So the order of the labels is not meaningful. In fact, like an interesting thing that I forgot to say about slot attention is that if you run the same example twice, the order of the slots is actually going to be different because they're sampled every time. So how well does it work? Well, it's competitive with baselines. So we compare against the deep set prediction networks. It's a recent paper which specializes on set prediction. And here we measure the average precision. And we have some distance threshold. So what we mean here is that detection is correct if the prediction of all the discrete properties of the object, such as color, shape, size, and material, are exact. And then we also predict the location of the object, the center of mass. And we have some threshold on the distance between our prediction and the ground truth. So when there is a distance threshold of infinity, means that we don't really care about predicting where the objects are, just what are their discrete properties. And the more we decrease the distance threshold, then the harder the task becomes. And now here, this is really like the vanilla implementation of slot attention. Like the deep set prediction network also introduces a bunch of tricks that they use, and you can use them on slot attention too. And if you do so, the performance actually gets quite a bit better. There are a lot of things here to parse, but what I want you to focus on is slot attention is all this like violet shape colored like bars, and the deep set prediction network is these gray bars. So if you care about just like raw performance, there are like tricks that one can add to make slot attention perform even better. But the main advantage of slot attention over things like the deep set prediction network is that slot attention is a very general module. It doesn't just do set prediction. It's something you can plug in the middle of your architecture to learn these abstractions. And another very nice thing is that object masks emerge during training. You can visualize what slot attention has learned by visualizing the attention masks. And the attention masks actually segments the scene in a like pretty meaningful way and achieve a pretty decent ARI score, which is a segmentation score. And now there are basically two things you can change. The first one is more iterations. So we train slot attention with 3 iterations, but then at test time, you can increase the number of iterations. And as you see in this bar plot on top, the performance typically goes up, meaning that slot attention generalized well to more iterations. And here on the bottom, you can see how the masks evolve during the different iterations. So here we have a very crowded scene. And we can see that at the beginning, after the first iteration, actually, there's already some specialization, but it's really not clear. And then the more, this is iteration 2, already objects start to emerge. And then the more you train, then the better the objects get separated between the slots. And this is lower resolution because we have strides in the encoder. Another interesting thing, which is actually not in the paper right now, I just wanted to show it, is that you can look at how the performance depends on the number of objects. So here we stratify the AP for different number of objects. So you see that less crowded scenes are easier to separate. But also you see on the plot on the right that for more crowded scene, having more iteration actually helps quite a bit. And so this indicates that, of course, having more objects is harder, but it also seems to require more reasoning steps to really be able to separate the objects in a meaningful way. And now the final interesting bit is that you can change the number of slots at test time. So you can train a dataset that contains maximum 6 objects and then generalize to exactly 6, 7, 8, 9, or 10 objects. And of course, the average precision goes down, like the task is harder, and you also go more out of distribution for like your clustering procedure. But the performance degrades gracefully. And the important thing here is that a task like this will not be easily solvable with the regular distributed representation. So even if I learn some neural network that learns to disentangle the object in the classical sense, everything I've done before, then I would not be able to change the number of objects to more objects in the training set because I'm bound to this vector structure with a fixed number of dimensions. While here, we have this common representational format for a variable number of objects. And this is really the key difference and what to me is the most interesting part. Then you can also do object discovery with slot attention. Again, the idea is the same. You have a CNN backbone, learn the abstraction with slot attention, and then you apply a slot decoder, and we use the same decoder from Iodine, which basically decodes each slot separately, and then at the very end learns a mask to also overlay the individual reconstructions. So this is how it looks on Clever 6. So the first column is the original input and the reconstruction, and as you can see, it's pretty crisp. And then you see the decoder masks and the reconstruction for each slot. So you can see here that each slot is neatly capturing like a single object. And we do this for other datasets as well, multi-disparate and this Tetris dataset. And we get results which are competitive with the state of the art. But the real advantage of slot attention here is that it's much more computer memory efficient than a state-of-the-art method like Iodine. So this makes it potentially more suitable if you then want to have like train an RL agent on the slots together with the actual like visual part. And again, it's important to stress that Iodine and Monet are specific architecture for object discovery, while slot attention is much more general. As we saw, you can also do set prediction, but these are just 2 example tasks. It's really a general module that you can plug in the middle of the architecture. Again, here we show that you can increase number of iterations and the performance measured in ARI goes up. Here we visualize the attention coefficient. So again, you see that at the beginning, after the first iteration, the objects are not yet split between the slots, but then as the iteration progresses, like they actually do split. And similarly for the masks. And interesting here, you can see that in the first row, although the attention is focusing on two objects, the decoder is still trying to reconstruct a single object per slot, but then it gets the shape a little bit wrong. So it's not, for example, slot 2 in the first part is not perfectly a cube, is something in between a cube and a cylinder, because it mixes up the two objects. It's pretty interesting. And again, we can train with maximum 6 objects and generalize to more objects and just by adding slots at test time. And as you can see, each object is captured in a slot. And sometimes the background is also captured in a single slot, but this doesn't happen all the time. And one can also do grayscale. So the ARI is basically the same, or like it's very close between the grayscale clever and the regular clever. So slot attention is able to perform this unsupervised segmentation even without relying on the color cues. So in conclusion, slot attention is a slot-based architecture, which I believe is very promising for learning abstractions and reasoning about these abstractions, and which we don't do in the paper, and this will be very interesting for future work. And it's based on attentive grouping. So in this kind of like clustering way, it acts as an interface between perception and these abstract representations. And a limitation of slot attention is that there's absolutely no hierarchy. So if you think about it as in the programming sense, slots are these variables that in principle can bind to everything. It's kind of like a general class that gets instantiated. But maybe we would want something which is slightly more hierarchical, where there is some specialization at the high level, and then you can instantiate multiple objects from the same class. So here we have a single class, and then we can instantiate as many objects as we want, but maybe we want to have multiple classes and instantiate multiple objects from this class. And also in slot attention, like the variables that we extract are task dependent. So what drives specialization is purely coming from inductive biases in the architecture and from the task. So this ignores inductive biases from the data side, which you could have, for example, if you had a video setting or there was some like actions involved. So for future work, I think it would be interesting to work on object discovery without autoencoding. A big limitation is since we use the same decoder as iodine, we have the same issues, meaning that the decoder is not very good to handle like textures. And so it works well on clever, but it's unlikely that it will work for like more complicated objects. And to really push it further, I think we need to get rid of this autoencoding part and maybe doing it in a contrastive setting. It will be interesting to explore other modalities, in particular point clouds, since slot attention can also do like this set to set. And as I said earlier, like going to the video setting and incorporating actions and training it jointly with RL agent. So also exploring different downstream tasks which go beyond the simple like classification or like reconstruction, but rather do control planning and reasoning, for example, by putting a graph neural network on top of the slots. Finally, scaling. We know that this type of architectures can scale better from Facebook is a great example. But we did not try to scale slot attention. And whether this will work or not, or you need to tweak the architecture a little bit, is unclear. And this is actually, in my opinion, also a very promising research direction. So thanks. We actually just released the code silently. So if you're interested, that's also the link where you can reproduce our experiments. Thanks.
Thank you.